In section 7.5, we are finding proportions in triangles, which is kind of a inappropriate name because we're not always going to be dealing with triangles in this case. But our first theorem and the second theorem really go hand in hand. Okay, the first theorem and the second theorem today go hand in hand. That's why the second one is a corollary of the first. But let's take a look at what they say here. All right. If a line is parallel to one side of a triangle and intersects the other two sides, then it divides those sides proportionally. So dealing with your triangle here, let me focus just on the triangle. If we give a couple of values here, let's go ahead and call this A and B, C and D. Okay? Dealing with those segments, the way the book asks you to do this, the book says, well, let's go ahead and take XR, which is B, over RQ, which is A, and that equals YS, which is D, over SQ, which is C. And that's fine. I mean, it can be done that way. Okay? B over A equals D over C. Or you can flip it around and say A over B equals C over D. That is fine. That works. The issue is I personally am a very pattern-driven person, okay? I learn better learning patterns, okay? And I see patterns easier than I just memorize stuff. So, in this problem, or these types of problems, what I prefer to do to set up my proportions, which it gives you the same correct answer, okay? I prefer to go between the parallel lines like this. I find it easier to see what I'm doing to go between like that. And then I have A over C equals B over D. And I just set up my proportions going left to right. A over C equals B over D. Okay? Either way that you want to do this is fine. It gets you the correct answer. It all depends on how do you feel comfortable setting up your proportion. Okay? The book wants you to do A over B equals C over D. I find it easier to go across in between the parallel lines. It is totally your preference. All right, let's take a look at this example down below. So we have parallel lines. That is the key here. And working it the way that I like to work it here is I would go between the parallel lines there and there. And so then I have 12 over 9 equals x plus 1 over x. 12 over 9 equals x plus 1 over x. So now I have my proportion set up. Let's go ahead and reduce our fraction, because we always want to reduce before we start cross-multiplying if we can, okay? I can take 12 and 9 and cancel out a 3. So 4 goes into there 3 times, and 3 goes into 9 3 times. Okay? So we have this, now I can cross-multiply. So 4 times x and 3 times x plus 1. 4x equals 3 times x plus 1. What's my next step? Distribute. Very good. And so we have 4x equals 3x plus 3. Subtract 3x from both sides. X equals 3. So let's take a look at the example right next to it here. Again, I've got those parallel lines, so the way I would like to set up my proportions is going between the parallel lines like this. And so I have A over 12 equals A plus 4 over 18. And I need to cross multiply. So I have, I'll move my work over here, 18A equals 12 times A plus 4. So 18A equals 12A plus 48. because I had to distribute. Subtract out the 12a. 6a equals 48. Divide out the 6. Okay, now, one reason I like to set my proportions up that way is because if I go down to this corollary, okay, they again want you to set it up like you did above, but now we have 3 sets of parallel lines. And if I put in some values here, let's call this A, B, C, and D. If I was setting up a proportion for this, I would go again between my parallel lines like that and say that I have A over C equals B over D. Again, that's what I find to be the easiest way to remember this. Okay? The book does it different. They're not wrong. It's still correct. It's just not as easy for me when I'm working a problem to see it that way. Okay? They would, of course, say A over B equals C over D, which is fine. It works. It's the same thing. Okay? Questions? No. All right, let's go to the backside. So the first 2 theorems were pretty much the same setup. Just go between the parallel lines. Well, our next theorem, they call it the triangle angle bisector theorem, theorem 7-5. In this one, looking at the triangle here, we of course have a triangle. It's not necessarily a right triangle or anything like that. It's just a triangle. And we have an angle bisector drawn through one of our angles. Okay? Notice that that angle bisector is dividing the opposite side into 2 lengths. C to D and then D to B. And so if I go through and give lengths here, let's call this A, B, C, and D, just giving it values that we can talk about. That opposite side going from C to B is now broken up into 2 lengths, D and C, right? Everybody see what's going on? Awesome. The way I would like to do it, the way I would like to set this up, the way I see it the most, the pattern again, looking for patterns, I find it easier to think about the left side of the angle bisector versus the right side of the angle bisector. And so I set up my proportions going along the angle bisector like this. And so I would say A over D equals B over C. Now, the book, they're not wrong. They're not wrong. They say that D over C, oops, that's not a C. D over C equals A over B. And that's fine. It'll work. Okay? Taking this segment, that value over that value equals this value over this value. There's nothing wrong with that. As far as patterns, though, seeing stuff, I personally find it easier to pair them up this way. It gives you the exact same answer. Okay? So I'm, again, just trying to help you find ways of memorizing this or remembering it so when it comes out time for a test or in the future if you're taking the ACT or NISA or whatever, you have these things in your back pocket. Okay? Questions on this theorem? Now again, we solve these exactly the same as we've solved anything else. Set up your proportion first, and then we cross multiply and solve. So let's take a look at this guy here. All right, you got to identify what situation you're dealing with. Well, in this triangle, we have an angle bisector. So of course, we're using that last theorem we just talked about. This line segment RS is broken up into 2 segments, 2 lengths. One is 10, one is 18. And so to set up my proportion, I would just stay to the left of the angle bisector and then go to the right of the angle bisector and say 10 over 12 equals 18 over x. I can simplify down 10 and 12 to 5 and 4. Oops, 5 and 6, excuse me. To 5 and 6, and now I cross multiply. So 5x equals, oops, we're going to need to do this little number crunching here. What's 6 times 18?
108.
108, which we now need to divide by 5. So x equals 21.6. 21.6. Okay. Questions on that? No? Looking at those last 3 problems, is there one of these you would rather see over another? Any example you want to see? The one right below it? Yep. Let's take a look here. Okay, now again, thinking of our 3 theorems we learned today, the first, we'll just call them the first, second, or third theorem. Okay, which one are we going to be using here? How are we going to set up our proportions? Okay, and again, this is why I want you guys to know the structure, the pattern. That's why I'm trying to show you patterns on these. You don't have to sit there and memorize which theorem it came from. If you see parallel lines, you know to set up your, hopefully you're learning to set up your proportions by going between the parallel lines. Right? So I have 10 over 30 equals x over, there we go, it's 15. They give us the entire length of that side is 45, but this length is 30, so the remainder there must be 15. Simplify your fraction first. So 1/3 equals x over 15. 3x equals 15, so x must equal 5.